So we were discussing the moment of inertia as in the linear motion. There is mass, and in terms of mass in the rotational motion, there is the analogy, you can say, it is moment of inertia. So for isolated or single mass, the moment of inertia will be mr square. Okay. If there are discrete masses like this, then moment of inertia will be like this. After that, we have discussed if there is a continuous mass. Continuous mass means, for example, a rod, or suppose I want to find the moment of inertia of this pen about any axis. I am not talking about the axis. So, okay. So any axis, you can find the moment of inertia of this pen about the axis passing from the end, about the axis passing from the center of mass and perpendicular to it, about this axis also, about any axis you can find. And this is what this is the not the discrete mass, this is the continuous mass. This is the continuous mass. And for the continuous mass, what we do, uh, integration. We use integration. Okay. So in the last class, I have discussed also moment of inertia of a rod about an axis which is passing from the center of mass and perpendicular to the rod, perpendicular to the rod. And this rod is a one-dimensional object. Means there is only length in the rod. We are assuming that there is only length in the rod, but in actual, you know that if you have a rod, there will be some thickness also of that rod. So but here we are assuming this is a one-dimensional object, and you can say this is a linear object. This have only the length. So the moment of inertia of the rod about an axis passing through the center of mass is m. M is the mass of the rod. Okay, m is the mass of the rod, L is the length of the rod. ml square by 12. So directly you have to learn directly. So ml square by 12. ml square by 12. Okay. After that, if same rod is there, you want to find the moment of inertia about the end, about the axis passing from the end of the rod and perpendicular to the rod. Then it will be ml square divided by 3. ml square divided by 3, I think. ml square divided by 3. So in the last, I will write down all the moment of inertia. Okay. And after that, I have told you if there is a ring, ring is also a linear body. If there is a ring, if you are saying a ring. So here we are considering that the thickness of the ring is negligible. So means it will be only, you can say, you take a thread and just round it like this. So it will become a ring. And it will have only length, 2 pi r will be the length. So ring will also be, you can consider a linear object. So we are finding out the moment of inertia of the ring as mr square. mr square. Now there is another object that is two-dimensional object, disk. So disk, we will calculate the moment of inertia of the disk. So moment of inertia of disk. So for example, this is a disk, suppose, and remember this disk is a two-dimensional object. So I am just showing this disk like this. This is a disk, okay. Okay, this is a disk. This have here also there is a material. In the ring, there is the material is on the periphery here. but this is a disk, so here also there is a material, and we want to find the moment of inertia of this disk about an axis. Whenever there is a moment of inertia to find, an axis should be defined about which you want to find the moment of inertia. So this is a disk. So about an axis which is passing through the center of mass of this disk and perpendicular to the plane of the disk. Perpendicular to the plane of the disk. For example, we can show that like this. This is a z-axis, suppose. This is a z-axis, suppose. Okay. And this axis is something like this. Suppose this is a plane of the disk and this axis is perpendicular to the plane of the disk. So moment of inertia of a disk about an axis passing through center of mass and perpendicular to plane of disk. Perpendicular to plane of disk. So as this is a disk, so how we will find the moment of inertia? This is also the continuous mass, and remember this disk is in the xy plane. This disk is lying in xy plane, so z-axis will be the perpendicular axis. So about the z-axis, we want to find the moment of inertia, and this is the center of mass here. Okay, so what we will do? In this case, we have to do the integration. We have to do the integration. So see how we will do the integration and what method we will use here. Okay, so I am taking a elemental ring. Elemental ring. So this is a elemental ring. And this is a very, very small elemental ring. And this elemental ring have the mass dm. So I am showing it here. I am zooming it. So I am showing. Basically, this is the elemental. I will zoom in. So at a distance of r, means this ring has the radius r, sorry, small r. Okay, so this is the center of mass, and from the center of mass at a distance of small r, we have just taken a elemental ring, and this elemental ring have the thickness this time, have the thickness dr. This thickness will be dr. Okay, got it till here? Any problem?
No, sir.
Now see. Okay, wait for 1 minute. To learn the moment of inertia of the, I know, I can also tell you the moment of inertia of the ring of the disk is mr square by 2, simple. But here now, what we want to learn, how to calculate the moment of inertia, how to calculate the moment. Topic is not that what is the moment of inertia. We know what is the moment. You will also know after some time what is the moment of inertia. But here that you should see what technique or how integration is helping to calculate the moment of inertia. This thing you have to analyze here. Okay. Okay. So this disk is a two-dimensional object. So it will have the area. This disk will be the two-dimensional object. This disk will be the two-dimensional object. So for the two-dimensional object, we define mass per unit area, sigma. We define the sigma. This is known as the mass per unit area. Maybe this is the new term for you, but this is very useful to calculate the moment of inertia and some other things also. Mass per unit area. What does it mean? In 1 meter square area, what will be the mass? That is this sigma. So in 1 meter square mass, oh sorry, in 1 meter square area, in 1 meter square area, the mass will be sigma. If I am saying 2 meter square area of the disk, sigma is the mass per unit area of the disk, mass per unit area of the disk. Okay, and remember this sigma is mass per unit area of the disk, and this is a constant value, and this is the constant value. This is mass, and area of the disk is pi r square. R is the radius of the square. Here I have to mention that m is the mass of the disk and r is the radius of the disk. Okay, so sigma is mass per unit area. So by the way, 1 meter square mass sigma, 2 meter square mass, 2 meter square area mass 2 sigma. Fine. Now we have this elemental area. We have this elemental area. Can you tell me what will be this elemental area? Hmm? Okay, so do one thing. Cut this from here. Okay, cut this from here and separate this like this. So basically, this is equivalent to this, and this thickness is dr, and what is the length of this strip? That will be 2 pi r. 2 pi r. So when you will open it, it will become a rectangle, and area, what will be the area of elemental ring? 2 pi r into dr, area of elemental ring. This concept is very important, okay, to learn. Is equal to, this becomes now rectangle, 2 pi r into dr. 2 pi r into dr. Okay, very good. We have find it out. If the area will be 1 meter square, then mass will be sigma. If area will be 2 meter square, then mass will be 2 sigma. If the area will be this, if the area will be this, that means area will be 2 pi r dr. 2 pi r dr area. Then what will be the mass? What will be the mass? Mass will be dm. Dm is the mass. Okay, you can. This is very elemental thing. So dm will be the mass. You have to assume small, very small mass. What will be the value of dm? Just tell me fast.
2 pi r dr sigma.
Very good. 2 pi r dr into sigma. Okay, and one more thing about the axis which is perpendicular to this, the plane of this. What will be the moment of inertia of this? What will be the moment of inertia of this ring? This ring I have just drawn here. So what will be the moment of inertia of this ring? Di will be the small moment of inertia. This is a ring now. So we know that the moment of inertia of the ring is
ml square by 12.
hmm, ml square by 12. No. Basically, you can see here. This is a ring, na? So what is the moment of inertia of the ring? M into R square. Simple. So this is a ring, na? So what is the mass? What is the mass? M into R square. Simple. So here you will write dm into R square. Okay. So you have just calculated the moment of inertia of this small elemental ring, and you will cut infinite number of small number of rings. Sorry. Uh, you can say that if you will add infinite number of elemental ring, then you will get a disk. So basically, you have just calculated the moment of inertia of this. Here also there will be a ring having different moment of inertia. Means you have to add the moment of inertia of the all the elemental ring contains by the disk. So for that purpose, there is a tool integration. There is a tool integration. So we will do integration. We will do integration, and from where to where you will put the limit from 0, because this smallest ring will be here and the largest ring will be here. So means this R is varying from 0 to capital R. So you will put the limit 0 to capital R. So the total moment the integration of di will be the total moment of inertia of this disk. So now put the value of dm. So it is 0 to r. What is dm? 2 pi into r into dr into r square. Okay. Now integration is there. Out of the integration, we will take constant term. We will take constant terms out of the integration. So 2 pi is constant and sigma is constant. So you can write 2 pi into sigma, and you will do the integration of 0 to r, and what we will have, r cube into dr. You can ask me one question, sir, why we have not done the integration here. There is a reason for that, because here is this dm. So either you should change this r in terms of m, mass. Okay, so same variable we do. Okay, the integration is we do the integration for the same type of variable. So that is why this mass I have changed in terms of the radius dr on and all that, by the way. So now can you do this integration? This is very simple. That day I have told you. Very good, very good. And when you will put the limit, what you will get? Capital R square divided by 4, because this there will be 0. No problem, very good. This is 2 pi, and sigma is mass per unit area. Area is pi r square. Okay. Mass per unit area of this disk. So mass is m. Area of the disk is pi r square. That is sigma. And when you will do the integration, you will get r to the power 4. R to the power 4 by 4, and you will apply the limits from 0 to r. Okay, so it will be 2 pi into m divided by pi r square, and when you will put the limit, you will get r to the power 4 by 4, upper limit minus lower limit. Now see which terms are getting cancelled out. Pi cancel out. This r square, here will be only r, and this 2. So what will be the answer? We have only m r square by 2. M r square by 2. So this is the moment of inertia of the disk about an axis passing through the center of mass and perpendicular to the plane. So the main motive to do this derivation is how to calculate the moment of inertia for the continuous bodies by using the integration. Otherwise, anyone can learn this mr square by 2 and all that. Okay, so please write down it fast. Then so remember this axis is perpendicular to the plane like this. If this is a plane of the disk, and this axis will be perpendicular like this and passing through the center of mass. So now here, how to decide I have to take the ring or all that. Just think, if you have a disk, okay, and if I am giving you a large number of small ring of small thickness, then if you will add all those rings, then there will be a disk. You will get a disk. Scroll down. Okay. So this derivation is, I am not saying this derivation is important, whether important or not, but the concept we have used here are important. So dm is the mass and dr is the thickness, remember. And putting the limit also is another thing. Accordingly, you have to put the limit here of integration. We cannot do all the derivation. Means we can find the moment of inertia of each and everything. Means we can find the moment of inertia of this also, this cup also. So main things we will do here. After this, now we will see cylinder. and cylinder is a three-dimensional object. But if you are taking a hollow cylinder, then okay. So for ring, okay, in the last I will conclude, no problem. So now we will see for the cylinder. Um, Cylinder. So first I am taking the completely hollow cylinder. Completely hollow cylinder. Completely hollow cylinder. Example, you can take the can. The Coca-Cola can be a completely. You can consider that. I am not saying that is a completely hollow cylinder. There will be some thickness also, but ideally you can just say that can be the example of completely hollow cylinder. The mass of the completely hollow cylinder is on the periphery only. So completely hollow cylinder, I am just so this is a completely hollow cylinder. I think now it's fine. And this is a completely hollow cylinder. Just try to imagine this like this. You can just imagine like this. Okay. If this is a hollow from inside, so the mass will be on the surface only. Mass will be or material will be on the surface only. Okay. So that is the thing. So for this cylinder, what we will assume to calculate the and basically we want to find the moment of inertia of the cylinder about this axis, about an axis, about this axis we want to find. Hmm. Okay, about an axis perpendicular to this area. Okay, completely hollow cylinder about an axis passing through the axis of cylinder. Okay, completely hollow cylinder, and we are finding the moment of inertia about axis of cylinder. So in this case, just try to imagine the mass will be on the periphery, on the surface. There will be a mass. You can take this example. The mass will be on the periphery only. Okay, from here and here, it is there is no mass. Okay, it is open cylinder. This is an open cylinder. Or you can say that this is not an open cylinder. This is a closed cylinder also. Oh, no, sorry. It is a open cylinder, not a closed cylinder. Okay, closed cylinder will be there in case of the solids, completely solid cylinder. So this is open from here cylinder. So how you will just calculate the moment of inertia here? Na, you have to assume a ring. Mm. You have just assumed this thing. So this will be a ring, a small elemental ring. Okay, this is a small elemental ring you have assumed. So what is this? This is a small elemental ring of mass dm, and radius will be the radius of the cylinder. Okay, so this r is the radius of this cylinder now. So r is the radius of the cylinder, and this cylinder have the mass m and radius r. So r is the radius of the cylinder. So what is this? This is the elemental ring. This is the elemental ring. Okay, so what we will do here, if I give you infinite number of elemental small elemental ring, and if you are placing one above the other, one above the other rings, one ring, another ring, another ring, another ring, then try to imagine, will you get a uh, completely hollow cylinder? Okay, if you will take infinite number of a large number of elemental rings like this, so you will get the completely hollow cylinder. So first what we will do, we will just we have just considered a small elemental ring, and for this ring first we will calculate what is the moment of inertia of this ring about this axis. So about this axis the moment of inertia of this ring will be very small, that is di. And what is the moment of inertia of the ring? Tell me the answer. About an axis, about this axis, na? About this axis we want to find. Tell me fast. Right. So mr square. Actually, it will be dm r square. So dm is the mass of the ring, okay, and r is the radius. So it will be dm into r square. Dm into r square. Elemental ring. Now it is very easy. We will do the integration. Do the integration both side, and di is the total moment of inertia, and r square, r is constant. You can see this is also r. If you will choose any ring on this cylinder, radius of that ring will be same. So r square is constant. Here you will have dm, and integration of dm means you are calculating dm on the whole surface. So you will get total mass, that will be r square into m. So what is the moment of inertia? Mr square. Moment of inertia is mr square. So moment of inertia of the cylinder about an axis, about the axis of the cylinder will be mr square. This is same as that of the ring. Of ring, there is the moment of inertia mr square. For the cylinder also, for the hollow cylinder, the moment of inertia is mr square. Now second, we will see the moment of inertia of means the for the solid cylinder. Solid cylinder. Solid cylinder. So solid cylinder, and the solid cylinder also have the mass m and radius r. So for the solid cylinder, na, what we will do, this will be closed from here. Okay, this will be closed from here. So imagine this is a closed or solid cylinder. Solid cylinder. So here you will assume an elemental disk this time. This will be the elemental disk, and same procedure you will follow for calculating the moment of inertia about this axis. So this is the elemental disk, and this disk has the radius r. Okay, this disk has the radius r and mass as dm. So about this axis, the moment of inertia of this disk will be, hmm, that is di will be dm by 2 r square, or dm r square by 2. So dm by 2 into r square. For the disk, the moment of inertia is mr square by 2. So here it will be dm into r square by 2. So we will do the integration to find the total moment of inertia of this cylinder about this axis. So it will become I, and r square by 2 is constant. Again it is dm. So integration of dm will be the total mass of the cylinder. So you will get mr square by 2. It is your, okay. So write down. If you will put a small disk one over the another, you will get the a solid cylinder. Okay. Now I have written some of the moment of inertia, means moment of inertia of some of the object. Uh, it will be a recap also and some additional also. And I think those moments of inertia are important or can be used. So you can write one by one. It is in one dimension. We have a rod. Okay, about this axis, the moment of inertia is the ring. This is ring. This is rod, one dimensional rod, and this is also the rod. Okay. Now after this, we have the rectangular lamina. Lamina means two-dimensional object. So this rectangular lamina have the length L and width V. Okay, so just wait a minute. I want to tell you how to learn the moment of inertia. If you want to find the moment of inertia about this rectangular lamina, about this axis, so you will write m into b square by 12. About this axis, m b square by 12. And about this axis, m l square by 12. Okay. And this is the disk. Okay. So write down. And this rectangular lamina have the mass m, length l, width b, small b. And this is the annular ring. Annular ring means this ring have some thickness here. Okay, this ring have some thickness and there is also the mass in this region. So this is known as the annular ring. So for the annular ring, the moment of inertia, and this is R1. R1 and R2 are the radius. Okay, so this radius suppose R1 and this radius from here to here is R2 and m is the mass. So the moment of inertia about this axis, an axis passing from the center of mass and perpendicular to the plane is m r1 square plus r2 square divided by 2. Scroll down.
Yes, sir.
Okay, so this is your completely solid cylinder, mr square by 2 about the axis of the cylinder. Okay, so write down this also, and after that you will have this annular cylinder, hollow annular cylinder. So this cylinder have some thickness also. At these points, okay, you can see two concentric circle type, and in between uh, two concentric circle region there is the material. So the moment of inertia will be m r1 square plus r2 square divided by 2. You can compare the moment of inertia of cylinder, hollow and solid cylinder, hollow cylinder with the ring and solid cylinder with the disc. Okay, write down. And here R1 and R2. R1 is the radius of this cylinder and R2 is the radius of this another cylinder. So there is one triangular lamina. Triangular lamina means this is also a two-dimensional object and this will have the area. If height is h, altitude of this triangle is h, and this is a base. So about the base, the moment of inertia will be mh square by 6. Okay, mh square by 6. So write down this also. And this is the sphere, hollow sphere. And for this hollow sphere, this is any axis passing from the center of mass. So the moment of inertia about that axis will be 2 by 3 mass of the sphere, and r is the radius of the sphere. And radius um, sphere is a three-dimensional object. About base means I want to say about the axis, this axis, x axis. So this is the hollow sphere here. You can take the example of hollow sphere like the cricket ball. Means not the cricket ball. Uh, you can take the example of hollow sphere as the ball of plastic. Plastic ball is there. So that is hollow. Plastic cricket ball. Solid also, but in that there is one hollow ball also. Scroll down.
Yes, sir.
Okay, so moment of inertia about any axis passing from center of mass of the solid sphere 2 by 5 mr square. Now see one thing. This is 2 by 3 mr square when you have the hollow sphere 2 by 3, and for solid is 2 by 5. So you can just here compare the moment of inertia of two spheres, like if here na, in this sphere, if this is the hollow sphere, so mass will away from the axis. So this here, the mass will be here. That will be at a more distance as compared to here. Here the mass is uniformly distributed, but here the mass is far apart. So what is moment of inertia? You can just compare a moment of inertia mass into r square. So r here will be more. So that is why this moment of inertia is more than this. Okay. Please write down this also. M is the mass, R is the radius of this sphere, solid sphere. Okay. After this we have a cone, hollow cone. The example of hollow cone you have seen in the birthday cap. Birthday cap is an example of a hollow cone. So the moment of inertia of the hollow cone about the axis of the cone will be mr square by 2. M is the mass of the cone, r is the radius of the cone. This r is the radius. R is the radius and L is the slant height. L is the slant height. After that, we have a solid cone. So solid cone, you can say that's the ice cream. Okay, filled with the ice. I mean the cone we got. We eat ice cream, na? So there is a cone, and if you will fill that cone with the ice cream, then it will become a solid cone. So solid cone moment of inertia is 3 by 10 mr square. 3 by 10 mr square. So write down this also. And in the next class, we will take some questions based on these moment of inertia. At least these moment of inertia you should learn. At least these. So we have three categories of object: one dimensional, two dimensional, and three dimensional.
So can you show hollow cone again?
Hmm? Hollow one. This.
Yes, sir.
Actually, both are looking same, na? So you have to imagine. Means this is a solid cone, so we can just paint it like this. Okay, so it will become now a solid cone. Okay, now it becomes the solid cone and this is the hollow cone. So for the hollow cone, the moment of inertia is m into r square by 2. So the moment of inertia is not depending upon the length L, means length height. And one more thing I want to add here, the moment of inertia of solid cone is less as compared to the hollow cone. The reason is same because here in case of the hollow cone, the mass is far apart from the axis, but here the mass is not far apart, all the mass is not far apart. Okay, so mass is uniformly distributed. So here all the mass is far apart, r is more, here r is less. Completed this?
Yes, sir.
Okay, so we can do one question. I think I have written here.